So, we continue our discussion of the Z transform and the Laplace transform. We shall look at these two transforms together, because typically an exposure to the Laplace transform is often expected in a course on networks. So when we handle electrical networks, we have either directly or indirectly been exposed to the idea of a Laplace transform, and we have used the Laplace transform as an operational tool. We were looking at the two transforms in the previous lecture, and the basic philosophy underlying both the transforms is that they generalize the idea of frequency representation to a more general kind of frequency, if you might want to call it that. The idea is that in the, when we talk about Fourier domain representation, we are thinking of the signal as comprised of a sum of sine waves essentially, and that's a limited representation because not all signals can be handled with that kind of a representation. Not all systems can be described by their Fourier domain or their frequency response. So, to broaden the class of systems and signals that we can handle in a transform domain, we wished to go over to the more general form of the eigenfunction, which led us to the Laplace transform and the Fourier transform. Although we have done this in the previous lecture and we already have an idea about the role of the eigenfunctions, let us look at both the transforms together from various perspectives now. Once again, first from the perspective of eigenfunctions. So, you see, what were the eigenfunctions, and now we'll keep writing them together. You see, we have continuous time, discrete time. Continuous time, the more generalized eigenfunction was e raised to the power of st, okay, going into the LSI system with impulse response ht, resulting in hs e raised to the power st, where hs is a Laplace transform of ht. We shall introduce some notation at this point. We will say that ht has the Laplace transform given by capital H of s. We will use script L to denote the Laplace transform. Similarly, for discrete time, the corresponding eigenfunctions were z raised to the power of n, which when passed through an LSI discrete time system with impulse response Hn, resulted capital Hz, z raised to the power of n. Yeah? And Hz was equal to summation over n Hn has the Z transform, which we will denote by script Z here, given by capital H of Z. So, the notation that we use is that the capital letter corresponds to the transform domain, as was the case before, and to the corresponding, if you have a small lettered sequence or a small lettered signal, corresponding capital letter corresponds to the transform. from the context, the transform is clear. I mean, if the signal is continuous time, then the transform must be the Laplace transform. If it's discrete time, the transform must be the Z transform. It could not be the other way. Now, we also had a relationship between these in a certain sense. We said we could think of these eigenfunctions here as sampled versions of these eigenfunctions. So, we could think of Z as e raised to the power st, where t is the sampling interval. So, if we happen to sample this eigenfunction at every multiple of capital T, we get this eigenfunction. That was the relationship that we drew. And we must take this relationship further, right? Must try and look at this relationship further. Now, of course, one thing that is common is that both transforms can be thought of as emanating from the eigenvalues corresponding to the eigenfunctions in the continuous time and the discrete time case. However, as far as the mapping specified by this is concerned, let us investigate whether it is 1 to 1 or many to 1 or 1 to many. Okay. In other words, is it invertible? So, let us look at this mapping a little more carefully. Yeah, so Z is equal to e raised to the power of st. Now, let us write down S and Z in a convenient form. We remember last time that one important point to be noted in the context both of the Laplace transform and the Z transform is that it is never complete to specify the Laplace transform or the Z transform by an expression. It is always an expression with a region of convergence. In the case of the Laplace transform, the region of convergence related to the real part of S. And in the case of the Z transform, the region of convergence related to the magnitude of Z. Right? Now, let us take a cue from there. So, therefore, let us write down Z in its polar form, r e raised to the power j theta. And let us write down S in its rectangular form. Yeah, so, e raised to the power sigma plus j omega times t. So, here we are, we have e raised to the power sigma t, e raised to the power j omega t. Now, when we make this identification, it becomes very clear what the relation between the S domain and the Z domain is. In fact, it is very clear that this has a magnitude of 1. So, this contributes only a phase. On the other hand, this contributes only a magnitude because it is non-negative. Irrespective of whether sigma is positive or negative, e raised to the power sigma t is always non-negative. So, it contributes no phase. Right? And therefore, it is very clear that r is equal to e raised to the power sigma t and theta is equal to omega t. Yeah. So, this brings into evidence this slight difference in the way in which we treat the S variable and the Z variable. Yeah. In the S variable, as expected, the real part influences the magnitude of the Z variable. Right? In fact, as sigma ranges from minus infinity to plus infinity, R runs from 0 to infinity. Right? So, as far as one way of looking at it is, there is a one-to-one mapping between R and sigma. Okay? However, we must be a little careful about theta. Now, of course, theta is equal to omega times t, but is it really a one-to-one mapping? Now, one must remember that theta is a rotating, it's a repeating variable, right? It's the behavior of theta is repetitive. It's if you plot the function z, if you fix r, and vary theta, yeah. So let's consider z is equal to r 0. Let's fix r and vary theta. Then it is very clear that z is a periodic function of theta, right? So there are many different omegas which can result in the same z. Yeah, so the mapping from omega to z, the other way, you see, for a given z, right, there are many omegas which can give you the same value of z. So in that sense, the mapping is not one-to-one. So if you look at the theta variable, or equivalently the omega variable, the mapping between the z plane, the z complex plane, and the s complex plane is not unique. In fact, this is a generalization of the fact that when you carry out sampling, you introduce periodicity on the frequency axis. In a sense, this is a manifestation of that, right? Another way of looking at the same thing is, if you look at z raised to the power of n, right? So, if z has a fixed magnitude, r0 e raised to the power of j theta, and theta varies, the whole raised to the power of n, okay? This is r0 raised to the power of n times e raised to the power j theta 0, theta n. Now, this is very easily shown to be equal to r0 raised to the power of n, e raised to the power j theta plus 2 pi n. It's very easy to show, right? We've done this before. When you introduce this, you just get a factor of e raised to the power j pi n, which is 1. What does it mean? It means there are several z's which really give you the same eigensequence. Right? There are several z's which really give you the same eigensequence in a certain sense. Several z's, if you look at it from the point of view of omega, right? If I think of z as a consequence of omega, of a particular s, there are several s's which will seem to give you several z's, and all of them really give you the same eigensequence, right? That is another way of saying that when I sample a signal, I lose some uniqueness there. Right? There are several sine waves which can have the same values at fixed points. For example, if I take a particular sine wave with zeros at particular points, right? So if I look at the points at which the sine wave passes through 0, there are an infinity of sine waves which will pass through zeros at the same points. That infinity is constructed by putting more than one cycle between those zeros, right? So the more cycles, what I mean is something like this. If I take this sine wave, if I mark what I call the zero crossings of the sine wave, there are several other sine waves which have the same zero crossings. For example, the next one would be this. And so on, right? And similarly, one can keep on constructing other sine waves which have a multiple of the half cycle between successive zero crossings, right? So that is the non-uniqueness that is introduced as a consequence of sampling, and that non-uniqueness is also manifested in the relation between z and s, right? Now, we shall not at this point go any further into this relationship between Z and S, save to understand this non-uniqueness that we have explained. But right in the beginning, it helps to understand that there is a relation between the Z and S plane in this sense, and the relationship has a non-unique component to it. All right. Now, going further, what are the other things that we looked at, and what are the other things that we need to build up? One thing that we saw was that, or at least the context of the Laplace transform, we saw that the idea of convolution carried over. So, when we convolved two signals, their Laplace transforms were multiplied, right? Now, let us establish the same property for the Z transform. Namely, if I convolve two sequences, and if each of the sequences has a Z transform, then the Z transform of the convolution would be the product of the Z transforms of the individual sequences. So, in other words, we could look at the following situation. Suppose we had a sequence xn. Let's not, this time for variety, let's not think of xn as an input and hn as an impulse response. Let's just consider the convolution. So, we have x convolved with h. Which is expressed by summation on k xk hn minus k. Let us call this sequence yn. We wish to find out the Z transform of yn. So, capital Y of Z is by definition summation on n yn Z raised to the power minus n. Now, this can be rewritten as summation on n, summation on k, xk, h n minus k, the whole multiplied by Z raised to the power minus n. Now, notice that the steps that we are following are very similar to the steps that we followed for the Laplace transform, except that the role of summation and integral is interchanged. So, what we did for the integral there is being done for the summation here. In a sense, it is easier to understand in the context of summation. Now, here we have a twofold summation on n and on k, and it is preferable to remove this expression n minus k. So, we have a different, let us introduce a different variable. So, now what we will do is, instead of having a summation on n and k, we will prefer to have a summation on k and some other variable where this becomes one variable. So, let us denote n minus k by another variable L. Now, once again the same reasoning. For a given k, when n runs over all the integers, L will also run over all the integers. So, a double summation on n and k with both of them running over all the integers is equivalent to a double summation on k and L with both of them running over all the integers. So, we might rewrite this expression as follows. Noting that n is equal to k plus L here. And now, once again we follow the same strategy. There are certain terms that depend only on k, which we shall bring out. The summation, the terms on L will be taken inside. So, we have summation on k, x k z raised to the power minus k, and in bracket summation on L, h L z raised to the power minus L. Now here again the same question arises, what z? What z? You see, we talked about the region of convergence last time. So for a given sequence, there is a set of z for which this expression converges. So there are two expressions involved here. So suppose we could find a z which lies in the region of convergence both of H, capital H, and capital X, then that z certainly is acceptable, right? So for the moment, let us assume that the region of convergence of capital X z and the region of convergence of capital H z have a non-null intersection. If they have a non-null intersection, we could choose a z within that intersection, and that could be the z here. And then we would have, now this is simply capital H of z, which is independent of k, it can be brought out, and this becomes capital X of z into capital H of z. And of course, the comment about region of convergence is that the region of convergence is at least the intersection of the ROC of X and ROC of H. All right, this is the minimum intersection this is the minimum ROC that we have. Once again, we must remember that the ROC could be larger. Okay, so it could happen that this process of multiplication results in a cancellation of causes that lead to the non-convergence of this in some region, right? So it could happen that there are some z's for which this by itself doesn't converge, but when you multiply it by this, convergence takes place. So that's the reason why here we are saying at least the intersection could be larger. That must be kept in mind. Okay? So here again we have the same interesting property in the Z transform, right? Namely that the convolution of two sequences results in the multiplication of their Z transforms. Now you see, as a consequence, we'd like to use the Z transform to define a quantity for a discrete time system. So you see, if you have a discrete time LSI system with impulse response Hn, and if Hn has a Z transform, that means what do we mean by saying it exists? It means that this converges in some region of the Z plane. There is a non-null region of the Z plane in which the expression converges, right? Then we can give this quantity a name. We can call Hz the system function, as we did for the continuous time case. So this is the system function of the system. And there again, if the input has a Z transform given by Xz, assuming the input has a Z transform, and the output has a Z transform given by Yz, it is clear then that Yz by Xz is a ratio independent of Z. Independent of X, independent of X, not independent of Z, and that ratio is Hz. What are we saying in effect? The system function is the ratio of the output Z transform to the input Z transform in a discrete time LSI system where the input and output both have Z transforms. Right? Have Z transforms means that there is a non-null region of the Z plane in which the expression for the Z transform converges. Now, you see, in a sense, what are we saying in this expression? Or what are we saying in the corresponding expression in the Laplace transform? Let us look at them together once again. So, here we are saying in a certain sense that yz is equal to xz times hz. So, let me write both these expressions together here. So, I will leave this expression as it is here, hz is the system function. I am also rewriting the expression for continuous time. So, I have ys is xs times hs, and we have from here capital Y of z. Of course, there are two different contexts. We must not mix the context. One is a continuous time context, the other is a discrete time context, but that is fine. There is a commonality of conclusion in both cases. What is the commonality of conclusion? One way to think of xz, or for that matter xs, is like a component of the corresponding signal xt or sequence xn on the eigenfunction z raised to the power of n in this case and e raised to the power of st in this case. That is one way to visualize this quantity or to interpret this quantity, a capital X of S or capital X of Z. There are two different contexts, remember, one must not mix the contexts. And similarly, these quantities Hs and Hz are in some sense the projections or the components of the impulse response along the same e raised to the power of st, the same eigenfunction, e raised to the power of st in this case or z raised to the power of n in this case. Right? So, what are we saying? The components of the output along a particular e raised to the power of st or z raised to the power of n depend only on the components of the input at the same e raised to the power of st or z raised to the power of n. And the relationship is that the output component is equal to the input component multiplied by the system component. What are we saying? In effect, there is a decoupled relationship between components. Now, this decoupling is what we call memorylessness, right? In time, whether in discrete time or in continuous time, the system may not behave in a memoryless way. But in the transform domain, there is a memoryless behavior. What do we mean by memoryless? We mean every value of the independent variable is treated separately. Now, this makes it very useful. That is another way of interpreting the transform once again. Yeah, we are introducing, we are removing rather the presence of memory. So, one can carry out the analysis of each of the components along e raised to the power of st or z raised to the power of n separately. So, naturally, the related question that arises is, well, after you carry out this analysis separately, can you reconstruct the original sequence or the original signal from its components? So, if I have y of s or if I have capital Y of z, can I reconstruct respectively y of t in this case or y of n in this case from the Laplace transform or the Z transform? Right? Well, of course, there is bound to be a method of reconstruction, because in particular, if the imaginary axis is a part of the region of convergence, then the Laplace transform is equal to the Fourier transform, and we know there is an inverse Fourier transform. Right? So, there is bound to be some method of reconstruction. In fact, let us take a cue from there. If we look at the Laplace transform, and if the region of convergence of the Laplace transform happens to include the imaginary axis, let's write down this idea here. Yes, so if we take the Laplace transform, so let's consider ys. right? Suppose ROC of Ys includes S equal to j omega, that is the imaginary axis. Yeah, then y of j omega is defined and it's equal to the Fourier transform, right? So y of j omega is then just the Fourier transform of yt. So of course, the inverse Fourier transform is written down very easily. We write down yt, and you see, in fact, here then we might ignore the j, right? So one might write down, if you allow me, let me write it down in the same notation. So then, if you write down the inverse Fourier transform, it would look like this. And there's another way of looking at this. There's another way of visualizing what we are writing here. Here, we are thinking of this as a real variable, omega. Yes? So you see, if you look at the S plane, what are you really doing? In the S plane, what are we doing? So let's visualize it. This is the S plane. This is the imaginary axis here. What are we doing in this integral in a certain sense? We are moving on the imaginary axis from the bottom of the imaginary axis to the top of the imaginary axis. So you could think of this as a motion on a contour, on a curve in the S plane. What kind of a curve? A vertical line in the S plane, starting from the bottom of the vertical line to the top of the vertical line. Right? Now that's what allows us to generalize. In fact, suppose the imaginary axis is not a part of the region of convergence, which is very, very common. We saw an example last time. Can we still invert the Laplace transform? Well, we expect that this should give us a Q. In fact, I shall now state the result without proof, because the result does depend a lot on an insight into complex analysis. Although I know that you have some exposure to complex analysis, I am not sure if we can really complete a very formal proof of what I am going to say, but it is not too difficult to understand the statement that I am making, so I will make it. Well, the statement is that in general one can invert the Laplace transform by integrating the Laplace transform multiplied by e raised to the power of st over a contour in the S plane given by a vertical line, and we move along the contour starting from the bottom to the top. All right. So what is the most general statement about inverse Laplace transform? Let me write it down. Y of t, whose Laplace transform is capital Y of S, is given by where the contour C is a vertical line in the ROC from bottom to top. All right. Let me give you an example. We saw last time that if we had the function e raised to the power of 2t ut, its Laplace transform was given by 1 by s minus 2 with a region of convergence real part of s greater than 2. Yeah. Now let's sketch this region of convergence. We have s equal to 2 here, right? And real part of s greater than 2 is this region. This is the ROC. Yes. Now, what does this expression tell you, or what could be a possible C here? Any vertical line here. That means C could be any contour S equal to sigma 0 plus j omega, right? Where sigma 0 is greater than 2, it's a real number greater than 2, and omega runs from minus infinity to plus infinity. That's what I mean by going from the bottom to the top. Is that right? And on this contour with this s, now you see s is a variable of integration now, and on this contour with this s, this yt, so e raised to the power 2t ut shall be equal to 1 by 2 pi j integral, well, omega running from minus infinity to plus infinity if you choose, or if you prefer it that way, 1 by s or sigma 0 plus j omega, yeah, minus 2 e raised to the power sigma 0 plus j omega t, right, and d again sigma 0 plus j omega, right. Now this is a way of writing this, but it is very rarely that you would evaluate it this way. If one does wish to evaluate this integral, it is easier to take recourse to methods in complex analysis. For example, you might have been exposed to the method of residues. So here one would invert this Laplace transform, one would evaluate this integral by evaluating the residues of the integrand in the region of interest, right. I shall not take the discussion on this inversion any further, save to state that this is the method in which one can invert the Laplace transform by taking recourse to integration in the complex plane. We shall derive a similar expression, or rather we will establish a similar expression for the inversion of the Z transform again in the complex Z plane in the next lecture. Right? So, thank you.